common belief during Galileo's time put the Earth stationary at the center of the universe, but Galileo defended the view of Copernicus, in which the Sun is central, with the Earth and other planets revolving around it. A typical argument against this idea was that if the Earth were moving, we would feel the motion, and a falling object would not fall straight downward. To counter this argument, Galileo developed his original principles of inertia and of relativity of motion. However, Galileo's original concept of inertia was different than what we're taught today. According to Galileo, planets would move naturally in uniform circular motion. Galileo was aware of motion in a straight line, or what is called rectilinear motion, but he argued that all such motion, even on the surface of Earth, is actually circular because the Earth rotates. Yet, Galileo's theory was inconsistent with Kepler's discovery. Kepler found that the orbits of planets are not perfectly circular. They are instead elliptical, and the speed of a planet changes along its elliptical path. Others, including Descartes and Newton, therefore modified Galileo's original concept of inertia. The most refined version of inertia was then codified by Newton as his first law of motion. Newton's first law states that a body at rest tends to remain at rest, and a body in motion tends to keep moving in a straight line at a constant speed, unless acted upon by an external force. Galileo's theory of planetary motion failed in its day, but nearly 300 years later Einstein described planetary motion as inertial motion. According to general relativity, planets are not pulled into orbits by force. Their paths are geodesics, or straight world lines in curved space-time. Einstein's theory is indeed more sophisticated than Galileo's theory, but still these two different concepts have a striking similarity. Both agree that planetary motion is inertial motion. Is it possible that Galileo's original concept of inertia is correct, but his theory of planetary motion is incomplete? If we assume Galileo's original concept of inertia is true, then what role does Newton's first law play in physics? Let's say that a body acted upon by an external force tends to move in a straight line due to the force, and therefore it tends to keep moving in a straight line upon removal of that force. In other words, Newton's first law is only a special case of his second law. Newton's second law states that when a body is acted upon by an external force, the body accelerates in the direction of the force. This holds true in a game of billiards. When a cue ball is hit straight on with a billiard stick, the ball accelerates and then continues to move in a straight line. But what about something like a ball twirling from a string? When a ball is pulled into a circular path of travel, the pulling force creates tension throughout the ball and string. As a result, the direction of the ball's momentum is held at a right angle to the force. Therefore, if the string breaks, the ball flies into a straight line of travel perpendicular to the force. The ball's tendency to move in a straight line has nothing to do with Newton's first law. It is caused by force. From this, we can assume that motion in a straight line is only a special case of Newton's second law, while generally everything in the universe moves about inertial frames of natural and force-free circular motion. Accordingly, the axial rotations of celestial bodies and their orbits are the products of inertia. So how can we explain special relativity and general relativity according to these principles of motion? In Galileo's model of the universe, all matter is bound with a circular type of inertia. All things, big and small, move about with an underlying rectilinear motion, but a body's momentum is carried and turned with a force-free spin from the body itself. Accordingly, the axial rotations of celestial bodies and their orbits are the products of inertia, both rectilinear and circular. A reasonable extension of this idea is the idea that all radiation transmits with a natural curve in its path. The curve is due to the circular motion of its source. Consequently, the faster a star rotates, the more curved its light becomes. The same kind of effect results from the orbit of a star. To see what happens with this sort of motion, suppose a star maintains a fixed straight-line distance from Earth. Any curve in the path of light will increase its length of travel from the source to the receiver, and the greater the curve becomes, the longer the distance will be. but because a greater distance of travel corresponds to a greater speed and a greater curve in the path of light, the elapsed time of travel from the source of light to the Earth remains constant. In other words, the motion of a star has no effect on the apparent speed of its light. Here, the apparent speed of light is defined as the magnitude of its average velocity. The average velocity for a curved path of light is equal to its total displacement divided by the elapsed time of travel. Consider the axial rotation of a star. The average velocity for any number of 360-degree rotations within a given period of time is 0, and so a logical assumption is that no degree of a star's rotation or its orbit will affect the apparent speed of its light. Galilean transformations incorporate the intuitive notion of addition and subtraction of velocities. The addition and subtraction of speed holds true with force-free circular motions, but a natural curve in the propagation of light works as a variable so as to maintain average velocity at magnitude c. The Earth is pictured at two different points of its orbit as starlight travels from a distant star. Light trajectories are shown as two curved arrows originating from the star. When Earth circles toward the star, the speed of starlight along its curved path of travel becomes faster relative to Earth. In the course of any given period of time, Earth will come across greater lengths of starlight. However, any degree of arc in the path of light is relative to Earth as well. For example, a straight path of starlight would be curved with reference to Earth because the Earth moves about an orbit of its own. By the same principle, a truly curved path of starlight becomes yet more curved relative to Earth as the Earth orbits toward the source of light. And so altogether, three things take place when Earth circles toward starlight. The speed of that light becomes faster relative to Earth. The Earth comes across greater lengths of starlight over any given period of time. And the curved path of that light becomes more curved relative to Earth. But because any change in the relative speed of light corresponds to changes in its length of travel and the curvature of its path, the apparent speed of starlight, or the magnitude of its average velocity, remains constant c relative to Earth. A similar but reversed process takes place when Earth circles away from starlight. As a result, neither the motion of a star nor the motion of Earth has any effect on the apparent speed of light. Based on these principles of motion, planetary orbits are described, at least in part, as a combination of rectilinear motion and circular motion. The Moon's orbit around Earth can be described according to these principles of motion. If we assume the axial rotation of the Moon is force-free, as envisioned by Galileo, then the Moon serves as a rotating inertial frame of reference. Thus, the Moon's orbit may have an underlying rectilinear motion, comparable to a geodesic, but its momentum is carried and turned with the Moon's rotation. As a result, the Moon circles about a full orbit with each of its 360-degree axial rotations. In such a case, the Moon's orbit is force-free, just as with general relativity, and yet it takes place in a setting of absolute space and time. The Earth's axial rotation can be explained in the same way. Individual particles of the Earth have underlying rectilinear motions, but each particle rotates freely so as to carry and turn the direction of its momentum with the Earth's rotation. The Earth's rotation then puts an imbalance of momentum upon everything within the Earth itself, while the imbalance of momentum creates a twisting force. As a result, a stone thrown to the air falls back to Earth, because the stone's inertial frame moves and changes direction with reference to Earth's rotation. The direction of its path progressively turns more directly toward the Earth, and as a result the stone gains speed as it falls. Other things, including the Coriolis force, also play a role in the effects of gravity. A dual spin by the entire universe, with one spin perpendicular to the other, would undoubtedly produce a multitude of inertial effects that could all be mistaken for gravity. These effects may include what are described by Kepler's laws of planetary motion. Large-scale effects of gravity could be the result of force-free circular motion by itself, while small-scale effects may occur due to a body's absorption of radiation from neighboring bodies. Imagine a large mass rotating in force-free circular motion. We can assume particles of radiation emit from the body in a straight line due to force, but still they maintain the free circular motion of their source. Hence, radiation travels in a curved path due to the force-free spin of a source. The strength of gravity therefore has a connection with the rate of a body's spin and the curved path of its radiation. The faster a body rotates, the stronger its gravity becomes, while a faster rotation also results in a greater curve in the path of its radiation. Now consider a satellite moving in close proximity to a planet. The satellite absorbs radiation from the planet, while angular momentum is transferred from the source of radiation to the receiver. This angular momentum has nothing to do with the intrinsic spin of elementary particles. Those spins likely cancel each other out because their directions are not aligned with one another. However, the angular momentum of radiation, due to the rotation of its source, is all of one common direction. The power of torque from this radiation is additive, and therefore it may rotate the position of a satellite along with its inertial frame so as to produce close-range effects of gravity. General relativity has long been on shaky ground due to its lack of compatibility with quantum theory. The ideas presented here are indeed highly speculative, but still they bring something curious to the drawing table. Effects of gravity produced by Galileo's version of planetary motion have striking resemblance to general relativity, while those same principles of motion pave the way to a quantum theory of gravity. Can it be that Galileo was right?